In 2003, a physicist named Max Tegmark published a paper. It was about parallel universes. The paper suggested that space is not just big, it's infinite. In an infinite space, everything that can happen will happen. It will happen an infinite number of times. This means there are other universes. In one of them, you made a different choice this morning. You wore a different shirt. In another, you pursued a different career. In countless others, you were never born. This idea is unsettling. It suggests every version of your life is playing out somewhere. It can make your own existence feel small. It questions the uniqueness of your choices, your successes, your failures. If every outcome is happening, what does your one life really mean? It's a deep philosophical hole to fall into. But while we grapple with the size of the cosmos and our place in it, the very act of looking up has given us tangible answers right here on Earth. The quest to understand those other potential universes has, ironically, made this one, our one life, better in thousands of small, practical ways. The drive to send people and probes into the void forced us to solve problems we never thought we had. It forced us to invent, to shrink, to perfect, and the solutions didn't stay in space. They came back down. They are in your kitchen, your car, your doctor's office, and in the device you're using to read this. The abstract pursuit of the universe gave us concrete tools. It grounded us. It shows that even if our one life is just one of an infinite number, the effort we make here has real, lasting impact. The technology we use every day is proof. Number 22, your phone's brain was forged by the moon race. The Apollo guidance computer used in the 1960s had a clock speed of about 2 megahertz. Your smartphone is over 1,000 times faster. In the mid-1960s, the Apollo program was buying so many integrated circuits that it accounted for 60% of all production in the United States. Without the moon race, the computer in your pocket would not exist in its current form. The problem was simple and impossible. To get to the moon, you needed a computer. You needed something to handle the navigation, the engine burns, the life support. But this was the 1960s. Computers were the size of rooms. They were filled with vacuum tubes that were fragile and generated enormous heat. You could not put a room-sized computer on a tiny Apollo capsule. You needed something small, light, and unbelievably reliable. A single mistake, a single failed component meant astronauts would die. The solution was the integrated circuit. The idea had been around since the late 1950s, invented by Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor. It put all the parts of a circuit, the transistors, resistors, and capacitors, onto a single tiny chip of silicon. This was a revolutionary idea, but it was expensive and difficult to manufacture. The commercial market was small. The military was interested, but it was NASA and the Apollo program that created the demand that changed everything. The MIT Instrumentation Laboratory got the contract to build the Apollo guidance computer. They did not build the chips themselves, they designed the computer and then placed massive orders with companies like Fairchild. This government money did two things. First, it funded the research and development needed to perfect the manufacturing process. Your companies learned how to make chips that were smaller, faster, and more reliable. They had to. NASA's standards were brutal. The chips had to work perfectly every time. Second, the huge guaranteed orders created a stable market. It allowed these young companies to scale up their production lines. This scale brought the price down. A chip that cost hundreds of dollars in the early 60s cost just a few dollars by the end of the decade. The Apollo guidance computer itself was a marvel. It was the first computer to use integrated circuits on this scale. The astronauts interacted with it using a simple keyboard called the D-Sky for display and keyboard. It had just over 70 kilobytes of memory. The programming was literally woven into the memory by hand. It was called core rope memory. Wires were threaded through or around small magnetic cores. A wire going through a core was a 1. A wire going around it was a 0. It was permanent, unchangeable software like a modern ROM chip, but built by hand. This massive push by NASA created the foundation for Silicon Valley. The engineers who learned how to make reliable chips for Apollo went on to start their own companies. The manufacturing techniques they developed became the standard for the entire industry. The price drop they achieved opened up the technology to everyone. After Apollo, integrated circuits started appearing everywhere. In calculators, in watches, in cars, and eventually in personal computers and smartphones. The intense pressure of the space race accelerated the development of the microchip by at least a decade. It forced an entire industry to mature at a speed that would have been impossible otherwise. So, when you send a text or check a map or take a picture, you are using a direct descendant of the technology that guided 3 men across 250,000 miles of empty space to land on the moon. Number 21, the invisible shield in your glasses came from a space helmet. The plastic used for astronaut helmet visors is called polycarbonate. It is incredibly strong and optically clear. But it has a weakness, it scratches easily. A scratch on a visor in space could be a disaster, obscuring an astronaut's vision during a critical spacewalk. Today, your own glasses are likely 10 times more scratch resistant than they were in the 1970s because NASA needed to solve that scratching problem. The challenge was clear. Space is not an empty, clean environment. Micrometeoroids and small particles of dust travel at incredible speeds. Inside the spacecraft, floating dust in contact with equipment could easily mar the surface of a plastic visor. Glass was not an option. It was too heavy and could shatter, so NASA needed to find a way to protect the plastic. The work happened at the Ames Research Center in California. NASA scientist Theodore Weideven was working on a system to purify water for spacecraft. His process involved creating a thin plastic membrane using an electric discharge of organic vapor. He realized that this same process could be used to deposit a very thin, very hard film onto another surface. The result was a microscopic layer of a carbon-based material, almost like glass, but applied to plastic. This layer was incredibly tough and transparent. It was exactly what was needed for the helmet visors and other plastic surfaces on spacecraft equipment. The technology was patented by NASA, but NASA's job is not to sell products. The agency has a technology transfer program. Its purpose is to make sure these inventions get out into the public and benefit the economy. In the early 1980s, the Foster Grant Sunglasses Company licensed the NASA patent. They saw the obvious application. People's sunglasses were always getting scratched. They applied the coating to their line of plastic lenses. It was a huge success. The technology quickly spread from sunglasses to prescription eyeglasses. Before this, if you wanted scratch-resistant lenses, you had to buy heavy, breakable glass ones. Now you could get lightweight, shatterproof plastic lenses that were just as durable. The coating process has been refined over the years, but the basic principle is the same one developed for astronauts. It is not just for glasses. The same technology is used on safety goggles for construction workers and lab technicians. It is on the face shields of firefighters. It is on ski goggles and motorcycle helmet visors. It protects sensitive instrument panels and display screens from damage. It is a simple, invisible technology that we now take for granted. But it was born from the very practical need to make sure an astronaut floating in the hostile vacuum of space could always see clearly. Every time you clean your glasses and notice they are free from the tiny scratches that used to plague older pairs, you are experiencing the benefit of a solution designed for the moon. Number 20, that perfect picture from your phone exists because of Mars. The camera in your phone uses a sensor called a CMOS active pixel sensor. It is the tiny chip that turns light into the digital picture you see. Over 90% of all cameras in the world use this technology. It was not invented for phones. It was developed at NASA's Jet Propulsion Laboratory in the 1990s because they needed a better way to take pictures of other planets. For years, the standard for digital imaging was a device called a charge-coupled device, or CCD. CCDs were good. They produced high-quality images. The Hubble Space Telescope used them, but they had big problems for interplanetary missions. They used a lot of power. They were relatively large and required other complex electronics to work, and they were sensitive to radiation damage, a big problem in deep space. For missions that had to travel for years and operate on tiny amounts of solar power, a better solution was needed. NASA wanted to build smaller, more capable probes. Faster, better, cheaper was the motto at the time. To do that, they needed smaller, better, cheaper cameras. A team at the Jet Propulsion Laboratory, led by an engineer named Eric Fossum, took on the challenge. He revisited an older technology called CMOS, which stands for Complementary Metal Oxide Semiconductor. This was the same basic technology used to make computer microchips. Early attempts to make image sensors with CMOS had resulted in poor image quality. But Fossum's team figured out how to solve the problems. They created what they called the camera on a chip. They integrated the light-sensitive pixels with all the amplifiers and analog to digital converters right on the same piece of silicon. This made the sensor incredibly compact. It used a fraction of the power of a CCD. And because it was built using standard microchip manufacturing processes, it could be made very cheaply. The new CMOS sensors were perfect for space. They were small enough to fit on tiny rovers and probes. They were robust enough to survive the journey, and they were efficient enough to run on solar power millions of miles from the sun. But the technology was too good to stay in space. Eric Fossum and some of his colleagues from JPL saw the commercial potential. They licensed the technology from NASA and started a company called Photobit to commercialize the CMOS sensor. At first, the market was small. They sold sensors for things like dental x-rays and industrial inspection cameras. The big camera companies were still using CCDs. The turning point was the mobile phone. Their phone manufacturers wanted to add cameras, but they needed something tiny, cheap, and power efficient. The comm sensor was the perfect fit. The demand from the phone industry drove massive investment and development. The quality of CMOS sensors improved dramatically, year after year. Soon they were not just good enough for phones, but for professional DSLRs and movie cameras. Today, CMOS technology is everywhere. It is in your webcam, your car's backup camera, your home security system, and the medical endoscope a doctor might use. It has completely changed photography and videography, making it accessible to everyone. All of this happened because NASA needed a more efficient way to get images of distant worlds back to Earth. The desire to see the surface of Mars led directly to the device you use to capture images of your own life. Number 19, your morning coffee is better because of the space shuttle. The process that creates much of the world's freeze-dried coffee was perfected for the Apollo missions. The original instant coffee was made by spray drying, which boiled away the water and a lot of the flavor. The freeze drying keeps the flavor intact. Neil Armstrong's first meal on the moon included freeze-dried bacon squares and coffee. The average American consumes over 1,000 cups of coffee per year, and a significant portion of the instant variety relies on this space-age process. The challenge was feeding astronauts on long missions. Food is heavy, water is heavy, and every ounce of weight on a rocket launch costs thousands of dollars. Regular food also spoils. For the early Mercury and Gemini missions, astronauts ate pureed food squeezed from tubes. It was not popular. For the Apollo missions, which would last over a week, NASA needed something better. They needed food that was lightweight, had a long shelf life, and was at least somewhat enjoyable to eat. The answer was freeze drying. The process itself was not new. It was developed during World War II to preserve blood plasma and penicillin without refrigeration. The process works by first freezing the food or liquid. Then it is placed in a strong vacuum. The vacuum lowers the pressure to the point where the frozen water does not melt into a liquid. Instead, it turns directly into a vapor. This is called sublimation. It is the same thing that happens to dry ice at room temperature. Because the water is removed as a vapor from a solid, the food's structure is left intact. The pores where the ice crystals used to be remain. This is why freeze-dried food is so lightweight and porous. It is also why it rehydrates so quickly. Just add water and the liquid fills those empty pores, returning the food to something close to its original state. NASA did not invent freeze drying, but they heavily invested in it and refined the process for packaged meals. They worked with companies like Whirlpool and Armour to develop a full menu of freeze-dried foods, from scrambled eggs to chicken stew. The goal was to remove about 98% of the water while retaining most of the nutrients and flavor. This made the food incredibly light and compact. An astronaut's entire food supply for a multi-day mission could be stored in a small compartment. After the Apollo program, the technology became much more widely known. Companies that had developed the expertise to supply NASA began looking for commercial markets. The first big one was camping and hiking food. Lightweight, non-perishable meals were perfect for backpackers. But the biggest market by far became instant coffee. Companies like Nestle, which created the first freeze-dried coffee in the 1960s, perfected the process. Freeze-drying coffee preserved the aromatic compounds that were lost in older methods. It resulted in a better-tasting instant coffee that dissolved easily. The technology is also used for other things. Pharmaceutical companies use it to make drugs more stable for shipping and storage. Biologists use it to preserve tissue samples, and of course it is still the basis for the astronaut ice cream you can buy in science museum gift shops. So the next time you make a quick cup of instant coffee, you are using a technology that was driven by the need to feed men on their way to the moon. It is a direct link between the grandest of human adventures and the simplest of daily routines. Number 18, the tool in your garage is a descendant of a moon drill. The first cordless power tool was developed for the Apollo program. Black & Decker created a cordless drill for astronauts to take rock samples from the moon. The battery and motor technology developed for that harsh environment was then used to create the entire consumer market for cordless tools that we know today, from drills to vacuum cleaners. Before the 1960s, a powerful tool needed a cord. Batteries were weak and heavy. They could not deliver the torque needed for serious work. But on the moon, you could not just plug a drill into a wall socket. Astronauts on the Apollo missions needed a way to drill deep into the lunar surface to collect core samples. These samples were crucial for understanding the moon's geology and history. The tool had to be powerful enough to drill through unknown types of rock. It had to be lightweight and easy for an astronaut in a bulky suit to handle, and it had to operate in the extreme temperatures and vacuum of space. NASA gave the contract to Martin Marietta to build the drill. They, in turn, partnered with Black & Decker to design the motor and power source. Black & Decker developed a special computer program to help design the electric motor. The goal was to get the maximum power out of the motor with the minimum battery drain. Every bit of energy was precious. They created a series of powerful, efficient silver zinc batteries to run the tool. The final product was the Apollo Lunar Surface Drill. It successfully drilled down 10 feet into the moon's surface on the Apollo 15, 16, and 17 missions. The technology did not stay on the moon. The research that Black & Decker had done for NASA was a huge investment. They had learned how to build powerful, lightweight motors and long-lasting battery packs. They realized there was a huge potential market for this on Earth. In 1961, they had released the first cordless drill, but it was for industrial use and not very powerful. The NASA project changed everything. Using the same principles they developed for the moon drill, they began creating a new line of consumer cordless tools. The most famous early product was the Dustbuster, a handheld cordless vacuum cleaner introduced in 1979. It used the same small, powerful motor and rechargeable battery technology. It was a massive commercial success and created an entirely new category of home appliance. From there, the market exploded. Cordless drills, saws, screwdrivers, hedge trimmers, and leaf blowers. The freedom from a power cord changed how people did work, both at home and on professional job sites. The technology continued to evolve with the development of nickel-cadmium and later lithium-ion batteries, but the foundation was laid by the Apollo program. NASA's need for a single specialized tool to explore another world directly led to an entire industry of tools that make our lives easier on this one. Every time you grab a cordless drill to hang a picture, you are using a piece of technology whose design lineage can be traced straight back to the dusty surface of the moon. Number 17, you can see inside the human body because we wanted to see the stars. The digital image processing techniques used in CT scans and MRIs were first developed at NASA's Jet Propulsion Laboratory. The goal was to take the faint, noisy radio signals from space probes and turn them into clear pictures. A CT scanner uses the exact same mathematical principles to turn a series of X-ray readings into a detailed image of your brain or organs. In the early 1960s, NASA was sending the Ranger and Surveyor probes to the moon. They sent back pictures, but the signals were weak and full of static and distortion. The raw data was just a stream of numbers representing different brightness levels. Engineers at the Jet Propulsion Laboratory had to figure out a way to clean up these images. They developed computer algorithms that could correct for the distortions, filter out the noise, and enhance the contrast. They could sharpen edges, bring out subtle details, and piece together multiple images into a single mosaic. This was the birth of modern digital image processing. These techniques allowed us to see the first clear, close-up pictures of the lunar surface. They were later used on the Mariner missions to Mars, revealing the planet's craters and canyons for the first time. The technology was a huge success for space exploration, but its biggest impact would be in medicine. At the same time, medical researchers were working on a new idea called computed tomography, or CT. The idea was to take multiple X-ray images of a patient from different angles. Each the 10th ray is a flat 2D image. But if you could combine all those 2D slices using a computer, you could reconstruct a 3D view of what was inside the body. The problem was, how do you do that? The mathematics were complex and the computer processing was intensive. It was the exact same problem JPL had already solved for its space images. The medical world adopted NASA's techniques. The algorithms that were used to clarify pictures of Mars were now used to create clear pictures of the human brain. Instead of combining radio signals from a spacecraft, the computer combined density readings from an X-ray detector. The result was the CT scan, which revolutionized medicine. For the first time, doctors could see inside the body in detail without surgery. They could diagnose tumors, internal bleeding, and other conditions with incredible accuracy. The same story is true for magnetic resonance imaging, or MRI. MRI machines do not use X-rays. They use powerful magnets and radio waves to get signals from the body's tissues. But just like with space probes and CT scans, the raw data is just a stream of noisy signals. And once again, it is the digital image processing techniques from JPL that are used to turn that data into the incredibly detailed images that doctors use for diagnosis. This technology transfer has saved countless lives. It is a standard part of modern medicine. It allows for earlier diagnosis and more precise treatment. It is a powerful example of how pure research, in this case the simple desire to see what another world looks like, can lead to profound benefits for human health. The computer code that once revealed the craters of Mars now reveals the inner workings of the human body. Number 16, you navigate by a clock that ticks at a different speed. The Global Positioning System, or GPS, relies on a fleet of satellites, each with an atomic clock on board. Those clocks run slightly faster than clocks on Earth due to the effects of relativity. To make GPS work, the system must constantly correct for this time difference. Without this correction, born from Einstein's theories about the universe, your GPS would be off by about 7 miles every single day. GPS is a military technology that became a civilian utility. It was developed by the U.S. Department of Defense starting in the 1970s. The goal was to have a robust, all-weather system that could give a soldier, ship, or plane its precise location anywhere on the globe. The system works through a constellation of satellites, currently around 31 active ones, orbiting the Earth. Each satellite continuously broadcasts a signal. This signal contains the satellite's exact location and the precise time the signal was sent. Your GPS receiver on the ground picks up signals from multiple satellites. It measures how long it took for each signal to arrive. Since the signal travels at the speed of light, the receiver can calculate its distance from each satellite. If you know your distance from 3 different satellites, you can pinpoint your location on the surface of the Earth in 2 dimensions, latitude and longitude. With a 4th satellite, you can also determine your altitude. The key to the whole system is timing. The timing has to be incredibly precise. A tiny error of just a few nanoseconds can throw off the location calculation by several feet. This is why each satellite has multiple atomic clocks, the most accurate timekeeping devices ever created. But there is a problem. According to Albert Einstein's theories of relativity, time is not constant. It is affected by gravity and speed. There are 2 relativistic effects at play with GPS. First is special relativity. The satellites are moving very fast, about 8,700 miles per hour. This high speed makes their clocks tick slightly slower than clocks on the ground. It is only a tiny amount, about 7 microseconds per day. Second is general relativity. The satellites are in a weaker gravitational field than we are on the surface of the Earth. And Einstein's theory says that gravity warps spacetime and clocks tick faster in weaker gravity. This effect is stronger than the effect from their speed. It makes the satellite clocks run faster than ground clocks by about 45 microseconds per day. When you combine the 2 effects, the clocks on the GPS satellites tick faster than clocks on Earth by about 38 microseconds every day. It does not sound like much, but if this difference was not corrected, the entire system would fail. A 38 microsecond error would translate into a positioning error of about 10 kilometers or 7 miles. Your GPS would tell you you are in the next town over. To solve this, the system is designed to account for relativity from the start. The atomic clocks on the satellites are intentionally set to run slightly slower. And the GPS receivers themselves have software that performs the final relativistic corrections. This connection to fundamental physics is what makes GPS so interesting. It is not just an engineering marvel. It is a daily, practical application of one of the most profound theories about the nature of the universe. The need to navigate on Earth forced us to build a system that has to obey the rules of space-time as described by Einstein. Every time you use your phone for directions, you are using a network of satellites that are living in a slightly different time frame than you are. Number 15, your house is protected by a space station. Fire alarm. The modern adjustable smoke detector exists because of Skylab. In the 1970s, NASA needed a way to detect fires or toxic fumes on America's first space station before they became a catastrophe. The result was the first smoke detector with a variable sensitivity, which could be adjusted to prevent false alarms. The technology was then spun off into the devices we have in our homes today. Early smoke detectors existed before the space program, but they were often large, expensive, and prone to false alarms. For a space station, you needed something better. In a closed environment like Skylab, an undetected fire could be fatal. But a false alarm that triggered the fire suppression system could also be disastrous, potentially damaging sensitive equipment or releasing harmful chemicals. The astronauts needed a reliable alarm that would warn them of a real danger but would not be set off by harmless things like dust or cooking fumes. NASA worked with the company Honeywell to develop a new type of smoke detector for the Skylab program. The key innovation was making it adjustable. It used a dual-chamber ionization system. One chamber was a reference sealed from the outside air. The other was open to the station's atmosphere. Radioactive americium-241 ionized the air in both chambers, allowing a small electric current to flow. If smoke particles entered the open chamber, they would attach to the ions and reduce the flow of current. When the current dropped below a certain level, the alarm would sound. The breakthrough was allowing the sensitivity of this trigger point to be changed. This meant the system could be fine-tuned to the specific environment of the space station, making it much less likely to have a false alarm. The Skylab mission launched in 1973. The new smoke detectors worked perfectly. After the program, NASA, as it often does, made its patents available for commercial use. The technology for the adjustable smoke detector was released to the public. This led to a new generation of smaller, cheaper, and more reliable smoke detectors for homes and businesses. The ability to adjust sensitivity meant they could be used in a wider variety of environments without constantly going off by mistake. The widespread adoption of these devices has saved thousands of lives. It is now a legal requirement in most places to have working smoke detectors in residential buildings. This is one of the most direct and impactful spin-offs from the space program. The need to protect a few astronauts living in a metal can orbiting the Earth led directly to a technology that protects millions of families in their homes every night. It is an invisible, silent guardian, beeping only when there is trouble, and its origins are in the sky above us. Number 14, the comfort in your shoes came from a moon boot. The shock-absorbing material and design concepts used in modern athletic shoes were pioneered for the boots astronauts wore on the moon. The Apollo moon boots needed to provide cushioning, support, and ventilation for astronauts walking in a low-gravity environment. Companies that worked on those boots later applied the same principles to create better sneakers for athletes back on Earth. An astronaut's boot is a complex piece of engineering. The boots worn by Neil Armstrong and Buzz Aldrin were part of their overall spacesuit, the A7L. The boot had an inner pressure bladder, just like the rest of the suit, to protect the astronaut from the vacuum of space. Over that, they wore a special overshoe for walking on the lunar surface. This overshoe had to do several things. It had to protect the astronaut from the extreme temperatures of the moon, which can range from boiling hot to freezing cold. It had to have a sole that would provide traction on the fine lunar dust, and it had to provide cushioning and support. Even though gravity is only 1/6 as strong on the moon, the astronauts were still carrying a lot of weight with their suits and life support packs. They needed a boot that would absorb the impact of walking and jumping. The boot was constructed in layers. It had layers of mylar and other insulating materials. The sole was made of silicone rubber with a tread designed for the lunar soil. But the key innovation was in the midsole and the overall construction, which was designed to allow for natural foot movement while still being a rigid, protective piece of equipment. The concept was called a spring damper system, designed to cushion the foot on impact and return energy, much like modern running shoes. A company called Avia, a maker of athletic shoes, was one of the first to explicitly market this connection. In the 1980s, they hired one of the engineers who had worked on the Apollo boot project. They used his expertise to develop a new line of shoes with better cushioning and stability. Other shoe companies also adopted similar concepts. The idea of using different density foams in the midsole to absorb shock, the external heel counters for stability, and the breathable materials for ventilation all have roots in spacesuit design. For example, the blow molding rubber technique used to create strong, hollow, and lightweight shoe soles was used by a NASA contractor. The company later used that same technique to create cushioned athletic shoes. It is not that a Nike Air sneaker is an exact copy of a moon boot. It is that the fundamental problems are the same. How do you protect a human foot from repeated impact forces while keeping it comfortable and stable? The extreme environment of space forced engineers to come up with novel solutions. Those solutions, the materials, and the design philosophies then trickled down to the consumer market. So, the next time you go for a run or play a game of basketball, the comfort and support you feel in your shoes is, in part, a legacy of the engineering challenge of taking a walk on another world. Number 13, some baby formula is better because of Mars. a nutritional supplement found in over 90% of infant formulas in the United States, was originally developed for a NASA-sponsored research program. The goal was to find a way to create a life support system for long-duration space missions, possibly to Mars. The research led to the discovery of a way to produce two essential fatty acids, DHA and ARA, from algae. The problem was how to keep astronauts healthy on a mission that could last for years. You cannot pack enough food for a trip to Mars and back. You need to be able to generate food and recycle oxygen and water along the way. This is called a closed-loop life support system. In the 1980s, NASA was funding research into this area. They were exploring the potential of using algae. Algae are amazing organisms. They grow quickly, they produce oxygen through photosynthesis, and they can be a source of food. The scientists at Martin Marietta, now part of Lockheed Martin, were looking at different species of algae to see which ones would be best for this purpose. During their research, they made an interesting discovery. They found a particular species of algae that was rich in an omega-3 fatty acid called DHA. They also found a fungus that was rich in an omega-6 fatty acid called ARA. These two fatty acids are critically important for human health. They are found naturally in human breast milk and are essential for the development of an infant's brain, eyes, and nervous system. Before this discovery, there was no commercially viable way to add these nutrients to infant formula. The formula was nutritious, but it was missing these key building blocks. The scientists realized they had stumbled upon something with huge potential health benefits right here on Earth. They formed a new company, Martech Biosciences, to develop the discovery. They figured out how to grow the algae and the fungus in large quantities in commercial fermenters. They developed a process to extract the oils containing the DHA and ARA. The result was a nutritional supplement that they named Formulate. In the 1990s, they began selling it to formula companies. At first, it was only in formulas for premature infants who are at a higher risk for developmental problems. But as the evidence for the benefits of DHA and ARA grew, it became a standard ingredient in nearly all infant formulas. The technology has expanded beyond baby formula. These same algal-based oils are now sold as nutritional supplements for adults. They are added to other foods, and they are used in animal feed to produce eggs and milk that are enriched with omega-3s. It is a remarkable story of unintended consequences. The search for a way to feed astronauts on their way to another planet led to a nutritional breakthrough that has likely improved the health and development of millions of children around the world. It is a perfect example of how investing in long-term, ambitious goals can produce unexpected short-term benefits that no one could have predicted. Number 12, firefighters are safer because of the space race. The lightweight, breathable air packs that firefighters wear, called self-contained breathing apparatus, or SPA, are a direct result of technology developed for the space program. Similarly, the heat-resistant fabrics used in their protective gear come from materials created for spacesuits and rocket components. Before the 1960s, a firefighter's breathing equipment was incredibly heavy and bulky. It often consisted of a heavy steel air tank carried on the back. This made it difficult to move quickly and added to the physical strain of fighting a fire. NASA faced a similar problem. They needed to provide astronauts with a reliable air supply for spacewalks, but it had to be as light and compact as possible. Every pound of weight was a major concern. NASA developed new technologies for lightweight air and oxygen tanks. They pioneered the use of composite materials like aluminum wrapped in fiberglass, which were much lighter than steel but could still hold air at very high pressures. They also developed more efficient regulators and harness systems to make the packs more comfortable and easier to wear. In the 1970s, the National Bureau of Standards and NASA launched a program to apply this aerospace technology to firefighting equipment. They worked with fire departments and equipment manufacturers to design a new generation of SCBA. The new packs used the lightweight composite tanks from the space program. They had better harnesses, inspired by astronaut designs, that distributed the weight more evenly. The result was a breathing apparatus that was significantly lighter, smaller, and more comfortable. A firefighter could carry the same amount of air in a pack that weighed 30% less. This meant they could work for longer and move more easily, which directly translates to saving more lives. The other key area of technology transfer is in materials. To protect astronauts from the extreme heat of atmospheric reentry and the intense temperatures of rocket exhaust, NASA developed a range of new fire-resistant fabrics. One of the most famous is a polymer called PBI, or polybenzoimidazole. It does not burn in air, does not melt, and stays supple even after being exposed to extreme heat. It was used in astronaut spacesuits after the tragic Apollo 1 fire. After the space program, this material was commercialized. Today, PBI is a key component in the outer layer of a firefighter's turnout gear. It is blended with other strong fibers like Kevlar to create a fabric that is incredibly tough and resistant to both heat and flames. This provides a crucial layer of protection in a fire. Other materials developed for things like rocket nozzle insulation and heat shields have also found their way into firefighting gear, from boots to gloves. The extreme demands of space exploration, protecting both humans and machines from fire and heat, created a whole new class of materials and technologies. Those same technologies are now used to protect the people who face those dangers every day in our own communities. Number 11. The computer mouse grew up in a NASA lab. The computer mouse was not invented by NASA. It was invented by Douglas Engelbart at the Stanford Research Institute, or SRI, in the 1960s. But it was early funding from NASA that supported his work and helped refine the concept into a practical tool. NASA was one of the first organizations to see the potential of interacting with computers in a more intuitive, graphical way. In the early days of computing, interacting with a machine was a difficult process. You had to use punch cards or type in complex text commands. It was slow and required a lot of training. Douglas Engelbart had a different vision. He imagined a future where computers would be used to augment human intellect. To do that, people needed a better way to interact with the information on a screen. His team at SRI began experimenting with different input devices. They tested light pens, joysticks, and trackballs. They also built a small wooden box with two wheels on the bottom, one for moving left and right, and one for moving up and down. A cable came out the back, which led one of his colleagues to nickname it a mouse. Engelbart's work was part of a larger project called the Online System, or NLS. This was a revolutionary system that included not just the mouse, but also graphical user interfaces, hypertext, and video conferencing. It was essentially a blueprint for modern personal computing. This kind of blue sky research was expensive. Engelbart needed funding. He got support from several government agencies, including the Air Force and ARPA, the agency that developed the forerunner to the internet. But a key early supporter was NASA. NASA was interested in Engelbart's work because they were facing their own information overload problem. They were designing complex spacecraft and needed better ways for engineers to visualize and interact with their designs. They saw the potential in NLS and the mouse as a way to make computer-aided design, or CAD, more effective. NASA funding helped Engelbart's team to continue their research and refine their ideas. They conducted studies to see which pointing device was the most efficient. The mouse won, hands down. It was faster and more accurate than any of the other options. The famous Mother of All Demos in 1968, where Engelbart publicly demonstrated the mouse, hypertext, and all the other features of NLS for the first time, was a landmark event in computer history. And it was made possible in part by the support of the space agency. After Engelbart's initial work, the mouse was further developed at Xerox PARC in the 1970s. It was then famously commercialized by Apple with the Lisa and Macintosh computers in the 1980s. But NASA's role was crucial. They provided the early stage funding and the use case that helped prove the concept. They recognized the importance of creating a more human-centered way of interacting with computers. The quest to design better rockets and spacecraft helped nurture the very tool that most of us now use to navigate the digital world every day. Number 10, that filtered water in your pitcher uses space station technology. The water filters used in many home water pitchers and portable water bottles are based on technology originally developed to purify water on the Apollo spacecraft. The need to provide safe, clean drinking water in a completely closed system forced the development of new filtration methods that are now used all over the world. The water is heavy. Launching it into space is expensive. For long missions, you cannot bring all the water you will need, so you have to recycle it. This means purifying everything, wastewater, condensation, even urine. For the Apollo missions, NASA needed a water purification system that was small, lightweight, and required no power. It had to be able to kill bacteria and remove any bad tastes or odors. They developed a system that used silver ions. Silver has natural antimicrobial properties. A small amount of silver ions released into the water can kill bacteria and prevent them from growing. The Apollo water system had a small device about the size of a pack of cigarettes that contained silver ions. As water passed through it, it was purified. This technology ensured the astronauts had safe drinking water for their entire trip to the moon and back. After Apollo, companies began looking for ways to use this technology on Earth. The problem was that the silver ion system was good at killing bacteria, but it did not remove chemicals or particulates. So they combined the NASA silver ion technology with another material, activated carbon. Activated carbon is a form of carbon that has been processed to have millions of tiny pores. These pores create a huge surface area. This large surface area is very effective at adsorbing or trapping chemical impurities like chlorine, pesticides, and industrial solvents. It also removes things that cause bad tastes and odors. The combination was perfect. The activated carbon would filter out the chemical contaminants, and the silver would prevent bacteria from growing inside the filter itself. This is the basic technology used in most common water filter pitchers, like the ones made by Brita. It is a simple, effective, and cheap way to improve the quality of tap water. The technology has also been critical in providing safe drinking water in developing countries and in disaster relief situations. Small, portable water filters using the same charcoal and silver combination can turn contaminated water from a river or well into safe drinking water. This has had a massive impact on public health, preventing the spread of waterborne diseases like cholera and typhoid. It is a clear line from a problem that had to be solved for a handful of astronauts to a technology that provides a fundamental necessity of life, clean water, to millions of people. The challenge of survival in space gave us a tool for better health on Earth. Number 9, those food safety rules in the supermarket were made for astronauts. The food safety system used by most food manufacturers around the world, called HACC, was originally created for the space program. NASA needed a way to guarantee that the food sent into space was 100% free of any pathogens that could make an astronaut sick. The resulting system changed how the entire food industry thinks about safety. Sickness in space is not just an inconvenience. It can be a mission-ending catastrophe. An astronaut with a severe case of food poisoning would be a medical emergency in a place with no doctors or hospitals. Vomiting inside a helmet during a spacewalk could be fatal. So for the early manned spaceflights, NASA had a critical requirement: the food had to be perfectly safe. The traditional method of quality control for food was to test samples from the end of the production line. You would take a few packages of food from a large batch and test them for bacteria. If they were clean, you assumed the whole batch was clean, but this was not good enough for NASA. This method could not guarantee that every single package was safe. There was always a small statistical chance that a contaminated package would be missed. To be truly certain, you would have to test every single package, which would mean opening them all up and leaving nothing for the astronauts to eat. NASA needed a new approach. They needed a system that did not just detect problems at the end of the process, but prevented them from happening in the first place. In the 1960s, NASA worked with the Pillsbury Company to create this new system. They called it Hazard Analysis and Critical Control Points, or HACCP. The idea behind HACP is to identify all the points in the food production process where something could go wrong. These are the critical control points. It could be the temperature at which the food is cooked, the cleanliness of the equipment, or the way the raw ingredients are handled. For each of these points, you set strict limits. For example, the food must be cooked to a specific temperature for a specific amount of time. Then, you monitor these points continuously to make sure the limits are never breached. If there is a deviation, you can take immediate corrective action. This proactive approach is much more effective than just testing the final product. It builds safety into the entire process. Pillsbury successfully used HACP to produce safe food for the Gemini and Apollo missions. After the program, Pillsbury started using the system in its own factories. In the 1970s, after several outbreaks of foodborne illness in the US, the Food and Drug Administration started to look at HACP as a model for the entire industry. Today, HACP is the international standard for food safety. It is used by meat, poultry, seafood, and juice processors. It is the foundation of the food safety regulations in the United States, Europe, and many other parts of the world. It has dramatically reduced the incidence of foodborne illness. So every time you buy food from a supermarket, its safety has been ensured by a system of preventative controls that was invented because NASA could not risk an astronaut getting a stomachache on the way to the moon. Number 8. Your car's tires are stronger because of a Mars lander. The material used to make the fibers that reinforce modern radial tires was first developed for the parachute cords on the Viking Mars landers. The material, 5 times stronger than steel by weight, was needed to survive the incredible stress of slowing a spacecraft down in the thin Martian atmosphere. In the 1970s, NASA was planning to send 2 landers to Mars as part of the Viking program. Getting them to the surface safely was a huge challenge. The Martian atmosphere is very thin, less than 1% as dense as Earth's. This means a parachute has to be very large and very strong to be effective. The spacecraft would be entering the atmosphere at over 10,000 miles per hour. The parachute had to deploy at supersonic speeds and withstand the massive forces involved. NASA needed a new material for the parachute suspension lines. It had to be incredibly strong, but also very lightweight. A chemist at DuPont named Stephanie Kwolek had recently invented a new polymer fiber. The material was part of a class of compounds called aramids. It was exceptionally strong and stiff. The company was looking for applications for it. Goodyear, the company building the parachute system for the Viking landers, tested this new fiber. It was perfect. It had the strength-to-weight ratio that NASA needed. This material was used to make the cords that connected the parachute to the lander. In 1976, the 2 Viking landers successfully touched down on the surface of Mars, a major triumph for the space program. The material proved its worth. After its success in the space program, DuPont and Goodyear began to explore other uses for this super strong fiber. One of the most obvious applications was in tires. At the time, radial tires were becoming popular. They offered better handling and fuel economy than older bias ply tires. The strength of a radial tire comes from the belts of material underneath the tread. These belts are usually made of steel. Goodyear realized that they could replace the steel belts with belts made from this new aramid fiber. The fiber-reinforced tires were just as strong as steel-belted ones, but they were lighter. They were also more durable and had better puncture resistance. The company began marketing these premium tires. Today, high-performance tires for cars, trucks, and airplanes all use aramid fiber reinforcement. The material's use has expanded far beyond tires. It is used to make body armor for police and military personnel. It is used in ropes and cables, in boat hulls, and in protective clothing for firefighters and race car drivers. But its first major application, the one that proved its incredible strength and reliability, was to safely lower a fragile robot onto the surface of another planet. The technology that protects your car's tires from blowouts was first tested in the thin red air of Mars. Number 7. The insulation in your home was made to protect astronauts. The shiny foil-like material used as a radiant barrier in many homes was first developed by NASA in the 1960s. This material, a type of metallized plastic, was created to protect spacecraft, equipment, and astronauts from the extreme temperature changes in space. Space is a world of thermal extremes. In direct sunlight, the surface of a spacecraft can get incredibly hot, hundreds of degrees above boiling. In the shade, it can plummet to hundreds of degrees below zero. Traditional insulation, like the fiberglass fluff you have in your attic, works by trapping air and slowing down heat transfer through conduction and convection. But in the vacuum of space, there is no air. The primary way heat travels is through thermal radiation. Everything gives off thermal radiation. Hot things radiate a lot of it. Cold things radiate less. To keep a spacecraft from overheating in the sun and freezing in the shade, you need to control this radiation. You need a material that reflects thermal radiation instead of absorbing it. This is where NASA's innovation came in. They developed a material that was essentially a thin sheet of plastic, like Mylar, coated with a microscopic layer of highly reflective material, usually aluminum. This material is an excellent radiant barrier. It reflects about 97% of the thermal radiation that hits it. NASA wrapped everything in this stuff. The Skylab space station was protected by a large umbrella-like radiant shield. The lunar lander was covered in it. Satellites and probes are still wrapped in these space blankets today. And astronaut spacesuits have multiple layers of this material to protect them during spacewalks. The technology was so effective and simple that it quickly found uses on Earth. One of the most well-known is the emergency shock blanket. These are the thin, crinkly, silver, or gold blankets that you see paramedics wrap around accident victims or runners use at the end of a marathon. They work by reflecting the person's own body heat back to them, which helps prevent hypothermia. But the bigger impact has been in construction. The same material used to protect the Apollo astronauts is now installed in attics and walls as a radiant barrier. In hot climates, it is installed with the shiny side facing out, reflecting the sun's heat away from the house and keeping it cooler. This reduces the load on the air conditioning system and saves energy. In cold climates, it can be installed with the shiny side facing in, reflecting the furnace's heat back into the house and keeping it warmer. It is a simple, passive technology that improves a home's energy efficiency. It has also been used to make insulated shipping containers, protective covers for cars, and even insulated tents for camping. It all started with the need to solve a fundamental physics problem, how to stay comfortable in a place with no atmosphere. The solution was a simple, shiny sheet of plastic that is now helping to keep our homes more comfortable and energy efficient. Number 6, a life-saving medical pump came from the space shuttle's fuel system. A tiny heart pump used to keep patients alive while they wait for a heart transplant was designed with help from NASA engineers. The engineers used their expertise in how fluids flow through rocket engines to help design a smaller, more reliable, and less damaging ventricular assist device. For a person with end-stage heart failure, a heart transplant is often the only option. But there are not enough donor hearts to go around. Patients can wait for months or even years for a transplant. During this time, their own heart is too weak to pump enough blood to keep their body alive. A ventricular assist device, or VAD, is a mechanical pump that can help the failing heart. Early VADs were large and they had a problem. The pumping action could damage blood cells, causing dangerous blood clots and other complications. The patient had to be on high doses of blood thinners. In the 1990s, a world-renowned heart surgeon named Dr. Michael DeBakey was working on a new, smaller design for a VAD. He wanted to create a pump that was more efficient and gentler on the blood. He partnered with NASA. It might seem like a strange partnership, but it made perfect sense. NASA's Johnson Space Center in Houston is home to some of the world's leading experts in computational fluid dynamics. This is the science of how fluids like rocket fuel move. To design a fuel pump for the space shuttle's main engine, you need to understand exactly how the liquid hydrogen and liquid oxygen will flow through the complex system of turbines and impellers. The goal is to move a massive amount of fluid very quickly and efficiently without causing turbulence or cavitation, which can damage the pump. This was exactly the same problem Dr. DeBakey was trying to solve, but on a much smaller scale and with a much more delicate fluid human blood. The NASA engineers used the same sophisticated computer modeling software they used for rocket engines to analyze the flow of blood through the proposed heart pump. They were able to simulate how the blood would move, identify areas of turbulence, and suggest changes to the design of the pump's tiny impeller. Their analysis helped create a pump that was much more efficient. The new design could pump the same amount of blood as older, larger devices, but with a rotor that spun much faster. This high speed created a continuous, non-pulsating flow that was much less damaging to blood cells. The result was the DeBakey VAD. It was about the size of a C battery, small enough to be implanted in a child. Because it was gentler on the blood, patients needed fewer blood thinners and had a lower risk of clots. The device successfully bridged thousands of patients to a heart transplant, keeping them alive and relatively healthy for months or years. It represents a powerful collaboration between medicine and aerospace engineering. The same fundamental principles that send rockets into space were used to give a failing heart a second chance. Number 5. The joystick you use for gaming was first a moon rover's steering wheel. The joystick, a common controller for video games and flight simulators, was first used in its modern multi-axis form to control the lunar roving vehicle on the moon. The Apollo astronauts used a T-shaped hand controller to steer, accelerate, and brake the electric vehicle across the lunar landscape. While simple joysticks existed before Apollo, the space program drove the development of the sophisticated, reliable controllers that became the standard for human-machine interaction. The challenge was designing a control system for a vehicle that would be driven by someone in a bulky, pressurized spacesuit. An astronaut's gloves are stiff and offer very little dexterity. A traditional steering wheel and pedals would have been impossible to use. The astronauts needed a simple, intuitive controller that they could operate with one hand. And NASA engineers at the Marshall Space Flight Center designed a T-handle joystick that was positioned between the two seats of the rover. It was a simple and elegant solution. Pushing the stick forward made the rover accelerate. Pulling it back applied the brakes. Pushing it to the left or right steered the wheels. A switch on the handle could put the rover into reverse. This single controller gave the astronaut full proportional control over the vehicle's movement. This was a critical piece of technology for the later Apollo missions. The Lunar Roving Vehicle, or LRV, was used on Apollo 15, 16, and 17. It dramatically increased the astronauts' exploration range. Instead of just walking a few hundred yards from the lander, they could travel for miles, exploring different geological features and collecting a wider variety of rock and soil samples. The rover and its joystick controller worked flawlessly. After the Apollo program, the concept of the joystick as a primary control device began to spread. The first major commercial application was in the video game industry. In the late 1970s and early 1980s, as home video game consoles like the Atari 2600 became popular, the joystick became the standard way to play. The simple, intuitive controls that worked for an astronaut on the moon were also perfect for a kid playing Space Invaders in their living room. The technology also became standard in aviation. Modern aircraft, both commercial airliners and military jets, often use side-stick controllers instead of a traditional control yoke. These are direct descendants of the systems developed for spaceflight. Joysticks are also used to control a wide range of other machines, from industrial robots and cranes to remotely operated vehicles used for deep-sea exploration. The need to drive a car on another world forced engineers to rethink how a person controls a machine. The solution they came up with, a simple stick that translates hand movements into action is now one of the most common ways we interact with the virtual and robotic worlds we have created. Number 4, safer highways and runways are a gift from the space shuttle. The technique of cutting grooves into pavement to improve traction and prevent hydroplaning was developed by NASA to make runways safer for high-speed aircraft landings. The same technique is now used on highways and roads all over the world, especially on sharp curves and bridges, and has significantly reduced the number of wet weather accidents. The problem was water. When an airplane lands on a wet runway, a thin layer of water can get trapped between the tires and the pavement. This can cause the tires to lose contact with the surface, a dangerous phenomenon called hydroplaning. When a plane is hydroplaning, it is essentially water skiing. The pilot has no steering or braking control. For a heavy, fast-moving aircraft like the Space Shuttle, a hydroplaning event on landing could be catastrophic. NASA's Langley Research Center in Virginia began studying this problem in the 1960s. They built a special test track to research tire friction on wet surfaces. Their experiments showed that even a small amount of standing water could cause a loss of traction. They needed to find a way to get the water out from under the tires. The solution they came up with was simple but effective. They used a machine with diamond-tipped blades to cut thin, shallow grooves into the concrete or asphalt runway. These grooves act as channels. When a tire rolls over them, the water is squeezed into the grooves and channeled away from the tire's contact patch. This allows the tire to maintain solid contact with the pavement, even in heavy rain. The technique of runway grooving dramatically improved braking performance and reduced the risk of hydroplaning. It was implemented at airports around the country, starting with Washington National Airport in 1967. It soon became a standard safety feature for major airports worldwide. The technology was not limited to aviation. Highway engineers realized that the same principle could be applied to roads to make them safer for cars and trucks. Hydroplaning is a major cause of traffic accidents. By cutting grooves into the pavement on accident-prone sections of highway, such as sharp curves, steep hills, and bridge decks, they could significantly improve vehicle control in wet weather. The process known as safety grooving has been shown to reduce wet weather accidents by as much as 85%. It also has other benefits. The grooves can help reduce splash and spray from other vehicles, improving driver visibility during rainstorms. The technology has also been adapted for other surfaces. It is used on dairy farm floors to prevent cows from slipping. It is used on factory floors and loading docks to improve safety for workers and forklifts. It is a very low-tech and straightforward idea, but the rigorous research and testing done by NASA to ensure the safe return of its aircraft provided the proof that this simple solution could have a major impact on safety back on the ground. Every time you drive over a grooved section of highway in the rain, you are benefiting from a safety feature that was pioneered to help land a spaceplane. Number 3, you can thank a satellite for today's weather forecast. Modern weather forecasting is completely dependent on a global network of weather satellites. These satellites provide the constant stream of data about clouds, temperature, and water vapor that feeds the computer models used to predict the weather. The first successful weather satellite, TIROS-1, launched by NASA in 1960, changed meteorology forever. Before satellites, weather forecasting was a difficult, ground-based science. Meteorologists relied on weather stations, balloons, and reports from ships and aircraft to get a picture of what the atmosphere was doing. This gave them a very limited view. They could only see the weather where they had instruments. They had no way of seeing the massive weather systems that form and move over the vast, empty oceans. This meant they were often surprised by major storms like hurricanes. The idea of using a satellite to watch the weather from above was proposed not long after the first artificial satellites were launched in the late 1950s. NASA, in partnership with other government agencies, developed the Television Infrared Observation Satellite, or TIROS. TIROS-1 was launched on April 1st, 1960. It was a simple satellite equipped with 2 television cameras. But what it sent back to Earth was revolutionary. For the first time, humans could see pictures of the entire Earth's weather patterns. They could see the large swirling cloud formations of cyclones. They could track storms as they moved across the ocean. The satellite operated for only 78 days, but it sent back nearly 23,000 pictures and proved that satellite meteorology was possible. The TIROS program was a huge success and led to a continuous series of weather satellites. Over the years, the technology has become incredibly sophisticated. Modern weather satellites do not just take simple pictures. They have instruments that can measure temperatures at different altitudes in the atmosphere. They can measure the amount of water vapor, the speed and direction of winds, and the temperature of the sea surface. They can monitor ice cover at the poles and track the path of volcanic ash. There are two main types of weather satellites. Geostationary satellites, like the GOES series, orbit high above the equator and stay fixed over the same spot on Earth. They provide a constant view of an entire hemisphere, which is ideal for tracking short-term weather changes and severe storms. Polar orbiting satellites fly much lower and circle the Earth from pole to pole. As the Earth rotates beneath them, they are able to scan the entire globe piece by piece, providing the detailed data needed for long-range computer forecasting models. This constant flood of satellite data is the lifeblood of modern weather forecasting. Without it, we would not have the 5-day forecasts we rely on. We would not have the early warnings for hurricanes and tornadoes that save lives. We would not understand the global climate patterns that affect agriculture and water supplies. The simple act of putting a camera in space gave us a godlike view of our own planet's atmosphere, transforming our ability to predict its behavior and prepare for its power. Number 2, that ear thermometer works like a telescope. The infrared thermometers that doctors use to take your temperature in a few seconds use the same technology that astronomers use to measure the temperature of distant stars and galaxies. NASA developed techniques for detecting infrared radiation to study the cosmos, and that same technology was then adapted for a fast, non-invasive medical device. Everything in the universe that has a temperature above absolute zero gives off thermal energy in the form of infrared radiation. Hotter objects give off more of it. Astronomers use this fact to study celestial objects. By measuring the infrared radiation coming from a star, they can determine its temperature, even if it is trillions of miles away. They use special detectors on telescopes, both on the ground and in space, like the Spitzer Space Telescope, to capture this faint infrared light. In the late 1980s, a company called Diatech was looking for a better way to take a person's temperature. Their traditional mercury thermometers were slow and breakable. Other electronic thermometers still required several minutes of contact. Diatech realized they could use the same principle as the astronomers. The eardrum, or tympanic membrane, is a very good indicator of the body's core temperature because it shares a blood supply with the hypothalamus, the part of the brain that regulates temperature. The eardrum gives off infrared radiation based on its temperature. If you could build a device that could accurately measure that radiation, you could get a precise temperature reading almost instantly. The company partnered with NASA's Jet Propulsion Laboratory to develop the technology. JPL had extensive experience in designing and building the sophisticated infrared sensors used in its space probes and telescopes. They helped Diatech create a small handheld device that used a lens to focus the infrared radiation from the eardrum onto a sensor called a thermopile. The thermopile converts the heat energy into an electrical signal, which is then translated into a temperature reading. The whole process takes just a second or two. The infrared ear thermometer was a huge success in hospitals and clinics. It was faster, safer, and more comfortable for patients, especially children. The technology has since become common in homes as well. The same principle is now used in non-contact forehead thermometers, which became very common during the COVID-19 pandemic. These devices measure the infrared radiation coming from the skin on the forehead. The technology has other applications too. Firefighters use thermal imaging cameras, which work on the same principle, to see through smoke and find people trapped in a fire. Home inspectors use them to find areas of heat loss in a building's insulation. It is a technology that allows us to see the invisible world of heat, and it was perfected by the need to understand the temperature of the most distant objects in the universe, then brought back to Earth to measure the temperature of something much closer to the human body. Number 1. You owe your life to a space program discovery. This statement is not an exaggeration for many people. The medical breakthroughs directly and indirectly linked to space exploration are numerous and profound. From life-saving imaging technology to surgical tools, the quest to keep a few people alive in a hostile environment has led to technologies that keep millions of us alive and healthy here on Earth. One of the most significant areas is medical imaging, as we saw with CT scans and MRIs. But the influence goes deeper. The charge-coupled devices, CCDs, that were developed for space telescopes like Hubble are also used in digital X-ray machines and mammography systems. They provide clearer, more detailed images with a lower dose of radiation than old film-based X-rays. This leads to earlier and more accurate cancer detection. Another critical area is remote monitoring. NASA needed a way to monitor the health of astronauts from the ground. They developed biosensors that could track heart rate, blood pressure, and other vital signs and transmit that data wirelessly. This is the foundation of modern telemetry in hospitals. The same technology allows doctors to monitor patients in the intensive care unit from a central nursing station. It is also the basis for a new generation of wearable health monitors that can track a person's health at home and alert a doctor to potential problems. Surgical tools have also benefited. The robotics developed for the space shuttle's robotic arm and for planetary rovers have been adapted for use in the operating room. Robotic surgical systems like the Da Vinci system allow surgeons to perform complex, minimally invasive procedures with greater precision and control. This leads to smaller incisions, less pain, and faster recovery times for patients. Even the study of life in zero gravity has led to medical insights. Research on bone density loss in astronauts has led to a better understanding and new treatments for osteoporosis, a disease that affects millions of people, especially older women, on Earth. The research on how the cardiovascular system adapts to space has provided insights into heart disease. The list goes on. Artificial limbs that use advanced materials and robotics from space technology, or lasers used in delicate eye surgery that use tracking systems developed for docking spacecraft. Water purification systems from the space station now used for dialysis patients. The space program is often justified by the grand goals of exploration and discovery, but its greatest legacy may be the unintended consequences, the solutions to small practical problems that, when brought back to Earth, have a massive impact on human health and well-being. It is the ultimate return on investment. The money and effort spent to push the boundaries of human presence in the universe have paid us back many times over in the most valuable currency there is longer, healthier lives.